Hello everyone. This report focuses on some very high-level decisions about radio technology called RFNoC. For source material, see the links in the notes. What is RFNoC? RF network on a chip. So radio frequency network on a chip. It's an implementation of radio stuff in FPGA hardware. What's an FPGA? It's a field programmable gate array. An FPGA is made up of what's called logic fabric. This fabric can be programmed by software that turns it into reconfigurable circuits that do specific tasks. Just like sewing, you start out with 8 yards of satin, and with skill and experience you end up with a wedding dress. If you don't know how to sew, it's a steep learning curve. And just like sewing, there's lots of different skills and techniques ranging from beginner to highly advanced. RFNoC is for FPGAs, what GNU radio is for general purpose processors. RFNoC is the GNU radio of FPGAs, and RFNoC operates underneath and with GNU radio. So why RFNoC? Why isn't GNU radio enough? Well, GNU radio might indeed be enough for us and many others, but we owe it to ourselves to figure out whether or not RFNoC is a huge win for us. Here's why RFNoC is such a big deal right now. Take something simple in theory. In the talk referenced above, the example given was something like a 200 MHz real-time Welch's algorithm implementation. While it might seem straightforward to implement this in an optimal manner, in practice there are several stumbling blocks. Operations that are crying out to be done in parallel and operations that can be done in basic math are ideal to shift to the FPGA, but the FPGA is underutilized. Transport between the blocks is overloaded. It's not optimized like at all. In the case we're talking about, we're targeting something like a USRP. Even with a high-end computer attached to it, the host just can't keep up with the demanding radio applications. Something like an X310 should indeed be able to handle this sort of implementation. RFNoC has great potential to eradicate this shortcoming. The goals here are several. Heterogeneous processing, where you have choices of composable and modular designs using general-purpose processors, FPGAs, and beyond. Maintain ease of use, that's a goal, and to have tight integration with GNU radio. The idea is to push the boundary between the general-purpose processor and the FPGA to the optimal place for whatever design you're implementing. Making FPGA acceleration easier is another goal, and the entire hardware stack being treated like a reprogrammable ASIC. Features of whatever you're working with are used as is. Essentially, the dream is to be able to select blocks and have the FPGA consume those blocks as easy as it is to select blocks in GNU radio and have your general purpose processor handle those. So RFNoC and GNU radio are considered to be a perfect match. The ideal way to use and test RFNoC is with GNU radio, seamlessly interconnecting with some caveats. One of the first caveats is something that many of us on the Phase4 ground team already know. That is, GNU radio has a steep learning curve, and RFNoC is very developmental. Things may change out from under you. A lot of groups, companies, and organizations are dabbling in RFNoC. People are eyeing each other from the shoreline, just waiting for the first few intrepid explorers to dive in. The building blocks are all there for this to happen. GNU radio is free. USRPs are available online. The X310 contains a big, expensive FPGA. It seems like everything is there to move flow graphs onto the FPGA in a more efficient way than we have so far. So why hasn't this already been done? Well, because it's hard. It takes a lot of time, it requires digital design expertise, and it needs transparent integration into software. This is a situation where you need a lot of radio domain experts. It's a fancy way of saying people that know about wireless communications. And you also need FPGA experts. Traditionally, there hasn't been a lot of overlap between these two groups. FPGA development is not really a requirement of communications engineering curriculums, and FPGA designers generally don't have a communications background. And the math is hard, and that affects everyone. RFNoC architecture consists of the user application being GNU radio. In the USRP, your source block, which is the USRP itself, it becomes an RFNoC source block. This new source controls the radio core. There is a USRP hardware driver, which is on the host PC. On the USRP FPGA, there's an ingress-egress interface and a crossbar. Below that, there's a radio core plus custom RFNoC blocks. RFNoC provides the communication infrastructure. The crossbar knows what to do with the data it's getting, and RFNoC provides space for user logic. That's the stuff that you design that's custom. For example, you might implement an FFT as an RFNoC block in an FPGA. You have an RFNoC shell. You put whatever you want into the shell. There's a big sticking point here with the tools available to us. FPGA tools are notoriously closed and expensive. RFNoC is all open source. Everything is available, but it's hard work and a steep learning curve. And finally, there are implications for dropping in something proprietary that you might have purchased, like a Xilinx IP core. Doing this for your own use is okay, but then if you were selling it to, say, a customer, then you have to check with Xilinx or whoever you got the IP core from. Since we're doing an open source radio, this aspect doesn't affect us as much, but it is something that a lot of companies have to consider as they move into this space. So the question is, should Phase4 ground be an RFNoC project? Should we bite off more than we can chew? Is it more than we can chew? This is what we need to be thinking about now, so that we can deliver a world-class radio that fits into the changing landscape of open-source software-defined radio. Comment and critique, welcomed and encouraged. What do you guys think?